folks. Pop over here. Hello, hello. How are we all doing today? Yeah. Okay. Switch cameras. Okay. Hi, Logan and Gabrielle on Twitch. Thank you all for coming. All right. Yeah. I just saw that emote. That's pretty great. That's accurate. Hello. All right. So let us hop in. We were talking about waves. Let's talk about waves. All right. Let me bigger. Can I make this? Okay, I'm gonna make it. Something over here. Okay, I'm gonna show you a wave. Okay, make this a little bigger. I know you can't see it. I want to get it right, and then I'll show it to you. There we go. All right. Oh, right. I forgot that this thing is incredibly messed up. Actually, that's not too much lag. Okay. Can everyone see this beautiful wave traveling? Hopefully, yes. Okay. So I'm going to ask you some questions about the parameters of this wave. So we had some things that we talked about. Bring my chat window up. We had some variables that we talked about last time with respect to a wave. So can you tell me any of those variables? Tell me what what the name of them is, and then what the value is. We're going to say each of these boxes is like 1 centimeter, right? Just for laziness. And we're going to presume it's going in real time. So the timer that's clicking on the side. So do you remember the variables, like what they were? Okay. In out of the gate with amplitude. Okay. Amplitude, wavelength. We haven't talked about starting point yet. We're going to talk about that later today, but yes. Amplitude, wavelength, period, excellent. All of those are good things. Okay, so let's go for amplitude. Amplitude, wavelength, period. Anything else? Frequency. Okay, there was one more I think we talked about. Let's see if you remember. Okay. All right, let's see if we can find some values for some of these things. Angular frequency omega. Okay, I lied. There's another one beyond that. So there were 2 more. Now there's 1 more. And some of these are connected. They're describing the same thing. Okay. All right, well, Ian came out with amplitude is 2 centimeters. Do you all agree, disagree? Do you think it has the 2 centimeter amplitude? 2 boxes. Yep. We're going to call box a centimeter and 2 boxes. Sounds accurate. Agree. Okay, sounds good. So we got amplitude. Check. All right. So how about some of this other stuff? What's the next thing we want to try to find? How about period? Can you tell me the period of this wave? What does period mean? Hard to see the wavelength. It is hard to see the wavelength when it's moving. And Logan also asked for pause. So we're going to pause it. And that's not a good place to pause it. Okay, and try again. All right. Can you give me an estimate? Okay. Skylar's got the equation that relates omega and t, so that is correct. So once we get t or omega, we get both. I have now paused it. What can you find now that I've paused it? Okay. What do y'all think? Ten and a half? 10 and a half looks pretty good to me. How did you get that? Logan says about 6. I don't think 6 is it. All right, distance between two crests. Does it have to be 2 crests? Nope. It could also be, if I started it moving again, we could do, right? We could do 2 troughs. We could do 2 points, right? We could do the point where it crosses the x-axis. There's one, I don't know if you can see my mouse. People on Twitch can see the mouse, right? Sorry, teams. You can do where it crosses the x-axis on the way up, and then it's going to cross the axis on the way down, but that's only half a wavelength. So it would be where it crosses the x-axis on the way up, right? Any of those. Any 2 points that are in phase. 2 troughs is a word. Yeah. Okay, sounds good. I like 10 and a half. Let's go with that. Okay. So what else do we need? We wanted period. I don't think we can get period with it paused. So let's go back to regular time. See if you can estimate the period for me. Two and a half, 3 seconds, something like that. Yeah. 1,000, 2, 1,000, 3, 1,000. I'm really bad at seconds. I think 3 seconds seems about right. 2.5 is probably more accurate. 2.5 seconds. Awesome. So now that we have, let's call it 3. I like 3 better. Sorry, Annie. So now that we have period, can we get frequency? Can we get angular frequency? I feel like I should be putting these in the chat, but I learned my lesson last time that it doesn't let me post in the chat for some reason. I think that's just too much for it. So if someone wants to take the initiative to put like A equals 2 and things like that. Okay. F equals 1 over T. So that would be 0.3 repeating cycles per second, also known as hertz. Looks good. Period 2.5. I went with 3. I don't know. Maybe it's 2.5. 0.7. 8 or 90. 95.8. 98 or something. It's really hard to tell. Ooh, I can do it in slow motion. Slow motion. There we go. Okay, it hits the peak at 108.7, I think. And I'm looking at the first red dot. Let's see. Okay. So hard to judge exactly when it hits the peak. 111.5. So what is that? 108.7 minus 111.5. Negative, it's 2.8. I think we can call that 3. I don't know. We'll find out in a minute because we can actually check this. Okay, so we found frequency. What about angular frequency? I don't know. We'll see because it's hidden below the line of the window. So when I scroll up, we'll find out who's right. Okay. Did we find omega? Yeah, 120 degrees per second is right. We just don't tend to use it. Hertz would be, the 1/3 hertz is more common for F. How about omega? What's omega going to be? It's using the 3 seconds, let's say. That's what I got. 2.09. What units is it? Units is tricky. Yes, radians per second. All right, so we have amplitude, lambda, period, frequency, angular frequency. There was one more thing that we talked about, which was the speed. So, how can we estimate the speed? First, is it going to the left or the right? That's important. Okay, V equals F lambda, frequency times wavelength. Excellent. So we can say it goes, or we can do also lambda divided by period. Logan came up with that one in the Twitch. That's also correct. And Noel, yep. So 10.5 over 3, and we get 3.5. 3.5 centimeters per second. So if we look at this, I can put it in slow motion to help us out. And looking at the time in the upper left corner, does that seem reasonable? Does it go roughly 3.5 boxes in 1 second? So let's see. Okay. So at precisely 260, okay, it was right there. So at 261, it is precisely right there. 1, 2, 3.5. Yeah, seems about right to me. Feel free to double check for yourself. Okay, let's scroll down and see if we were right. Put it back into real time. Okay, frequency. 120. Oh, it's because it's not in a box. It's not a centimeter, I think. All right, 0.376, 2.66 seconds. I think Annie was slightly better. So clearly 1 box is not 1 centimeter. And it doesn't really tell you that. So can we work out what 1 box is? That would be nice if it told me how many boxes in a centimeter. Let's see. It is going up 2 boxes, but it's quite clearly not going 128 centimeters per second. Right, it's not going 128 boxes in a second. So I guess the vertical boxes are centimeters and the horizontal boxes are not. That's my take on it. Let's see, we got 10.5. They got 340. 340.5 divided by 10.5. Huh. It's like 32 centimeters per box. That's really weird. Well, we got the right frequency. Yay. I didn't realize that it was doing not 1 centimeter. Okay. Misleading measurement. It is a faulty graph. Yeah. It is a lesson in labeling axes. So that actually leads me very nicely into the next topic, which is I cannot give you a thing like this on a test because it's moving, and we are not in the Harry Potter universe, and I cannot print moving pictures for you. It's very sad. It's amazing to teach physics in that kind of universe. Anyway, so instead, I have to give you a graph that is frozen. There are two ways to do this. The simple way is to hit pause, right? And then, actually, I'm going to move this into Edge. Do not judge my use of internet browser. I realize Edge is not best. But I'm moving it into Edge because Edge will let me draw on the picture. That is my goal here. Okay, I want to use the interactive simulator. Bigger. Bigger. Can I type or do I just have to drag? Just have to drag. We were at 0.376. Close enough. And we were at 128. Roughly. Okay, close enough. Okay, close enough. So can I draw? Nah. Maybe I can't draw. Bigger, 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 bigger. Pause. Aha, I can draw. Okay. So there we go. I can draw. Woo. Axes. Okay. In defiance of their command, I'm going to label these because that makes much more sense. I object. 6, 8, 9, 10. Okay. Do not judge. I 36 tabs. I actually have an extension that suspends all of the tabs that I'm not using because I realize that's a problem. Also, did you know that mobile Safari will only let you open 500 tabs? I learned that last weekend. Okay. So how should I label this axis? What am I measuring? I know, right? Only 500, I know. So it's not going to be wavelength, although we can use it to measure wavelength. So both of these axes are going to be in centimeters. There's fat pen here. This thinner. Yeah. Okay. So that's probably why my phone doesn't work either. What variable should I put in these axes? X, Y, T, F, lambda, T, V, Z, I don't know. E. E, that's interesting. Could be E. It would be E if it was an electromagnetic wave or it's like an electric wave. But we don't know what kind of wave this is. It could be anything. Y-axis is kind of hard. So my question is, what should I put? What should I put here? What should I put here? All right, I'll help you out. This can be X, or it can be S, or Y, or whatever the physical axis, right? We're not going to label it lambda because lambda is something we are measuring on this graph. It's not the axis itself. It's not that this is 1 lambda, 2 lambda, 3 lambda, right? That's weird. On the y-axis, we're going to call this capital D. In this graph, we're going to do x as centimeters. You could do radians. Um, although that would be a different type of graph, I think. That would just be a regular sine graph. Like, you would get nothing useful out of that if x was radians. You would just get your distance between two crests is 2 pi. You're like, all right, I already know that. So what does the d stand for? Displacement. You're correct. Sorry. I mean, it's not, it doesn't give you any additional information. Radians are super useful for waves. We're going to talk about radians all the time. But if you put your axis in radians, you're literally just going to get like 2 pi. Okay, so we have our y-axis displacement. So that can be displacement for sound wave. It can be displacement for Slinky. It can be like ocean wave. It can be electromagnetic fields. Right? It can be anything. So D is our default. Right? D for displacement. Sorry, Andre. I didn't mean to like. Okay. So and then my lambda would be like from here to here. That would be lambda, right? Or I could do from here to wherever it happens next. That would be lambda. It would give me an answer in centimeters. Okay. Does all make sense? Right. This is something called a snapshot graph. Can I just, yeah, I can. Snapshot graph. Okay. It is displacement versus position, and it is a snapshot of a wave at a specific moment in time. Right? I hit pause. This is the snapshot graph at precisely however many seconds. Right? Get out of the way. Put it up here. There we go. No, I can't put it there because then I can't unpause it. Can I make this smaller? No. All right, it can just live there. If I hit, oh. Can I go back? No. Sorry, I'm having technical. Oh, I can just minimize it. That helped. I'm going to go back. Save. That's fine. Let's exit my doodles. Oh, well, that didn't work. Well, what I was hoping to accomplish, but I am having technical problems, is to show you that if I then take that same wave and it's like 76-ish. Got it. This is like 128-ish. Close enough. If I pause it here, I now have a snapshot graph at t equals however many seconds. I send it going some more. I now have a snapshot at t equals, it was 4.4 something seconds, right? And it looks different, right? So snapshot graph is going to be a specific moment in time. Let us actually go to OneNote and then I can. Oh. Where's OneNote? OneNote is not open. It's okay. How many windows can I open at once? Okay. Alternately, there we go. Waves. Okay. alternately, I can do what is called a history graph. Okay, wait, let me write down what I wrote down about snapshot graph first. Snapshot graph is displacement versus x or y or s or whatever. It is a picture at a specific moment in time, t equals something, and you can get lambda from it. Okay. Our alternative is something called a history graph. From context, what do you think a history graph is? Just going to share my desktop because it's getting annoying. Like a histogram, but with waves. I think it's interesting. I think it's a really interesting thought. I think you're thinking too hard again. Graphs past behavior, right? You're showing the history of the behavior of, it's the history of the behavior of a specific point. So at some x equals something, right? It's not going to be x on the axis. What do you think the horizontal axis is going to be? What's it, the ordinate axis? I forget how it works. Horizontal axis is going to be what? It's going to be position? It's going to be something else. I have a nice little animation actually for that one too. Nope. Nope. Well, I thought I had a nice little animation for it. I definitely opened a nice little animation. Couldn't find what I was looking for. That's something before this. Oh, I guess not. I'm sure I did this. Did I just like not save it? Nope. Nobody's told me what goes on the horizontal axis yet. There we go. But that's not the one I wanted. Well, that's pretty close. It would be time. You are correct. I know what I want. New bad stuff. Had a really, this one, which looks almost the same, but yet is subtly different in a way that is important to me. Okay. Oh no, it's right there. Okay. So our particle, it went away. Come here. There we go. Our particle is the little dot in the center that's going up and down. Right? This actually isn't. This is what I wanted. It's close enough. So you think about the thing in the center going up and down, right? As it goes up and down, it sort of corresponds with a point on that wheel. And as it goes, we're drawing out the history of what it was doing over time. Does this make some sense? The issue here is that it looks exactly the same. It's just a sine wave. So, t versus time, they both look almost identical, right? But the difference is, if I measure from this crest to this crest, what am I going to find? Am I going to find the wavelength? Am I going to find something different? You're close. Think about what this axis is measured in. Time. Usually it's in seconds. So when this was meters, we would get lambda in meters. If this is seconds, we're going to get a value in seconds. That's not usually frequency, that's usually what? You're very close. Not quite there. Getting colder. What's one of these variables that we measured in seconds? Logan has it over on Twitch, but I think Noel. It is the period T. Is what you're gonna get. Like my Easter colors. It's pretty. Okay. Does that make sense? Right? It's at a peak at T equals 2 seconds. And then at 3 seconds, 4, 5, 6, 7. Now at 8 seconds, it's back up at its maximum. So what is the period? Period would be 6 seconds. That's how long it took to make one complete trip. Making sense? Positive emotes. Aha. That's good. Okay. It makes sense. Yay. Okie dokie. Okay. I think I'm doing okay. So they will look the same for a sine wave because they're symmetrical. When will they not look the same? They will not be identical for asymmetric waves. So this is something like maybe like a triangle wave that's not symmetric, or like a sawtooth. Oop, deleted my sawtooth. Come back. Come back. My sawtooth, right? Sawtooth is not symmetric. So I have a little thing to demonstrate that over an edge. How many windows can I have open at once? All of them. Okay. So we're back to our old friend. This thing. Whoops. Okay, we're gonna exit out of that. Don't save. Exit. No. Okay. Don't load. You were already loaded. Okay, no end. Manual. So I'm going to do this in slow motion. So I'm going to make a slow rise and then sharp down. So I made an asymmetric wave pulse that is traveling along. I don't want any damping. Do normal. So we're going to do slow. We're going to do slow rise and then down. Right? So we have an asymmetric thing moving along. Think about that green dot right when it goes through the window. Right? What does it see first? So this is slow down. Right. From the point of view of the window, it sees the slow rise go through, and then the sharp down, and then the other down. Right? So what would the history graph look like? The history graph would show you, so the snapshot looked like, my computer is like, what are you trying to make me do? You have so many windows open. Okay. Come on, it's 2020. We can at least have functioning computers. Come here. Everything else might be somewhat apocalyptic, but I demand my futuristic technology work. Okay, forget it. And I'm pretty sure we crashed. Nothing's happening. What do you think the history graph versus the snapshot graph are going to look like? My tabs are innocent in this. Looking for a scapegoat. Yeah, it's definitely dead. Will Control-Alt-Delete still work? I could go either way. Nope. Alt F4, okay, I'll try it. Nope. RIP. Press F to pay respects. I know what Alt F4 does. I have to do a hard reboot anyway, so. Right, I'll try Control Shift Escape, and if that doesn't work, we're gonna hold a hard reboot. Nope. Rip. I didn't know, I just thought it was a good idea. Hard reboot. I'm so sorry, Surface. I apologize. Okay. We're gonna try that again, but all right. Don't worry about that. If we have a scrap of paper. I'm a very organized individual. Okay, here we are. We have a wave going past that is asymmetric. Right? From the point of view of this side of the screen, it sees, right, as this approaches, it does the slow rise and the sharp fall. So if we were to draw the history graph, it would look, what? There's one key word here. It would show me the slow rise and then the drop. So if I graph that along a time axis, I don't think that's what you meant to write. All right, it's logging me in. It'll be there in a second, right? So the first thing you will see is on the, right, now I'm not sure if my camera is flipped or not, right? It shows you slow rise first and then the drop. Tell me which way this is going on your screen. Is it going to the left or to the right? On my screen, it's going to the left. Okay, for you, it's going to the right. Okay, that's exactly what I wanted. Meanwhile, Logan sees, oh God, you see it the other way because Twitch is showing you this screen. Oh, for God's sake. We're just gonna wait for this to boot up. I'm really sorry, technical difficulties. I need that like thing to pop up and just be like, do, 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 do. Okay. All right, we're getting there. I won't open as many tabs this time. I don't need Chrome anymore. I don't need Edge anymore. I'm just gonna open Teams and OneNote. Oop. Fine. Do not open WebEx. God, WebEx. Why are you so terrible? Fine. And share my screen. Okay. So we have a wave where if we froze it, it looked like this. Actually, it looked like it was like a slow rise, and then it went, nah, nah. That was what it looked like, right? Does the graph be affected? How fast they pass. So yes, the speed of the wave will affect how smushed or extended your graph is, but you can also change the axes. So it doesn't make a huge difference. It doesn't make a big difference in the appearance, but it'll make a difference in terms of like the actual numbers. Right? Does that make sense? So this is the snapshot. So if I were to plot a point right here over time, its displacement over time would look like a slow rise and then a sharp fall and then flat bit and then another fall. What is the key word for how this is different? Reflected? Yeah. I was looking for backwards, but yeah, reflected is totally more smarter backwards. Okay. This, right, so that makes sense. What about if I had a another crazy graph? So let's do like a sawtooth looking guy. Like a shark fin. Yeah, let's do shark fin. Shark fin. And this time the shark fin is traveling to the left. What would the history graph look like? So this is a snapshot. Snapshot. This is history. Would it be reflected or would it be the same? It would be the same. So it would be, ooh. Can I draw the same thing twice? No. If it were moving to the same thing, same snapshot, but it was moving to the right, the history graph, snapshot, history, it would look like this slow rise and then that. It'd be reflected. So yes, so Skylar says it's only reflected if it is going to the right. That is correct, because in our right-centric world, we declare that time is going positive as it goes in this direction. So, yeah, because of the fact that we're always drawing our time axis to the right. It's like a weird convention thing. Okay, let us keep going. So now we have some beautiful graphs. So we talked about pretty pictures, we talked about beautiful graphs. Now let's talk math. Specifically, I want an equation. I'm going to type. No, type. Type. Fine. I guess you don't want to let me type. So Skylar asked, we never have a negative axis because that's impossible. Not really. I mean, you could declare like, oh, I am looking at this in rewind. Or you could say, oh, time increases as we go to the left. This is 0 seconds, this is 2 seconds, this is 4 seconds. But you automatically look at that and go, ugh. It's just because our convention, which I believe goes back to Descartes, is that positive is to the right, because people are left-handed, people are right-handed, left-handed people are evil. No, it's fine. I kid. I wish I was left-handed. I'm not special. T minus 10 seconds. Although that's still going forwards, it just starts at the negative and then comes to 0, which could go that way. All right. So we want an equation that, now it'll let me type, an equation to tell us that is the world's tiniest font. I'll make it bigger. There we go. Particular location is doing at a particular time. Smooth brain. Sounds like it's a reference to something, but I don't know what. So what we want to do is have a displacement as a function of both x and t. So I will say, oh, at a position 2 centimeters along at t equals 5 seconds, is it a crest? Is it a trough? What's it doing? Right? So can you tell me roughly what type of equation this is going to be? Am I going to do something linear, quadratic, a sine, a quartic, an exponent, a power series? Like, what exactly is this going to look like? Hint, it is probably easy. Don't think too hard. What is the structure of this equation? I guarantee you that at least 8 of you have thought it, and you're just not saying it because, I don't know. It is parametric, that's true. It's a function of 2 different variables. But I want to know, is it like, do I need to do like x squared plus t squared, or do I want to do something weird? Like, do I want to do e to the x, or do I want to do something else? So Andre says probably sine. You are correct. Sine. Why do we do sine and not cosine? Because sine comes first, I guess, in SOHCAHTOA. Doesn't matter. Sine of some stuff. Okay. What goes here? Damn. Tangent looks different, so it doesn't get to be tangent. Annie is great. Puns. So, amplitude. Yes, you're both correct. Amplitude goes here. If your amplitude is 1, your sine wave is going to go from positive 1 to negative 1. If your amplitude is 3, it's going to go from positive 3 to negative 3. It's what goes right here. So, amplitude. Okay. Then we have to think about, do you remember how sine waves work? I don't know why you thought omega t. It's weird. Everything else is going to go inside this sine. So now we have to remember, how do sine functions work? Oh, ho, ho, ho. We're not doing triangles, we're not doing circles, we're doing functions. So I lied. I'm going to open Edge because I only have 2 tabs and I can close it. Oh, I didn't want to close both of them. I wanted to close one. There we go. Let's do, oh, don't look at the news. Okay. Oh, now you can't see that. Haha, you didn't get to see the news. That's so nice. I am tempting fate. I live on the edge. Okay. So, let's see. What does sine of x look like? It's beautiful. What type of graph is this? Snapshot of history. Skylar says snapshot. Ian says snapshot. It is snapshot because it is not a function of time. It's a function of position, right? Because we did X. Annie, you're technically right. It could be both, right? But because I put X here, we are presuming that this is the X-axis, and thus it is a snapshot graph. Okie dokie, sine of X. Can you tell me the wavelength of this wave? Hmm. 6.25. It's really close to 6.28, which Andre has noticed is, if I click right here, oh look, it's 2 pi right here. Oh. Pi over 2. The next one should be at 5 pi over 2. Okay. How about if I do sine of, what happens if I do 2 pi times x? We can zoom in a little bit. Can you tell me the wavelength of that wave? Okay. How about if I do sine of pi times x? These are getting hard to see. There we go. How about this one? 2. Okay. So with your excellent skills of predicting, can you tell me what you think? Here, let me do this. If I did pi, pi over 2 here. Tell me what you think the wavelength is going to be of sine pi over 2x. It's 1/2 or 4. Ooh, this is tricky. Okay, let's see. 4. Okay, what's the pattern here? Do you see the pattern? What if I do sine of 2 pi, divided by, let me move the x out, x, pi over 6. Oh no, migraine, geez. What on earth? It's like a monkey whose brain is exploding? Wow. In my day, we just had like colons and parentheses, and that's all we had to work with. All right, 2 pi over the value. So yes. Am I showing the desktop or am I showing? So just show desktop. Okay. All right. Oh. So we have essentially our equation dx of t equals a sine 2 pi over lambda times x. Okay. I'm going to help you out by saying the next bit, there's a plus or minus, and that gets us something times t. So the reason we do this is because if this bit is, say, 0 for some reason, we still have sine of some stuff times t, right? Or if we have t is 0, we would still have sine of some stuff times x, right? So we want them to be added rather than being multiplied or anything like that. Okay, pattern recognition time. Can you tell me what goes in this spot. We're going to talk about K in a minute, but K doesn't go here. Are y'all just looking at the formula sheet, or do you know why it's omega? Formula sheet. To isolate the radians. Yeah. So based on pattern recognition, right, this bit, right, what went in front of X, right, the stuff in front of X was this stuff in front of X was 2 pi divided by essentially the distance between crests on a snapshot graph, right? That was the wavelength. So the stuff in front of the T, what is that what for? In front of T is 2 pi divided by the distance between crests on a history graph. Distance between crests on a history graph is the period. So here we put 2 pi over lambda. Over here we put 2 pi over capital T. We already know this is omega, right? Angular frequency in radians per second. So when we multiply omega times T, we just get radians. Okay. What about looking at the formula sheet? What goes here? It goes right here. Now it's K. K is called the wave number. And it is essentially measured in per meter. So that when we, or you can think of it as radians per meter, although it's not really common to see it written that way. Meters to the -1. So when we do K times X, we just get radians. Right. Making sense? Yes. So if we think about our equation that we had way back at the beginning of the class, right, we had 2 centimeters was our amplitude, sine of 2 pi. This was, our wavelength was 10.5 centimeters. Our omega was 2.09 radians per second. I'm gonna leave this as an unknown for now. Okay. Does this make sense? Yes, you. Yes, you. Send me a happy emote if this makes sense. I think what I'm going to do, I'm going to post like a little Canvas quiz to help you practice writing the equation for stuff. There's some on the final exam homework too. But it's really easy once you put this stuff together. Let's talk about, this is something that we didn't properly talk about, which was we got V by doing lambda over T or by doing lambda times F. So this was 10.5 centimeters over roughly 3 seconds. We're really estimating here. And then this would be 10.5 centimeters times 0.33 hertz. get the same answer. I can also do one. Yeah, Noelle sent me an email about this. I'm sorry I didn't answer it yet. I'll talk about it at 4:45. That's okay. Really, I could talk about it now because there's really no answer. There is homework, but I'm not sure what it'll do. So yeah, stand by for that one. Can we make an equation that has omega and k in it? Is it going to be like omega over k, omega times k, k over omega? You know, it's not the last one because I had to stop and think about it. So is V option A, option B, option C, option D? Which of these do you think it is? Okay. 2 votes. Sorry about my squeaky chair. I'm going to put that on my to-do list right now. Unsqueak the chair. Okay. I want to see what the rest of y'all think. You want a little bit longer? Yeah. Do I have any? I might have some. I have glue. I'll just like dump glue on it. That's how you fix squeaky chairs, right? I don't want it to wobble. Okay. I now have 3 votes for A. 4 votes for A. That's good because the correct answer is A. Ah. Duct tape does fix everything. Wow, that's impossible to see. A is the correct answer. So, which makes sense because omega is 2 pi over t divided by 2 pi over lambda, right? That's the same as doing 2 pi over t times lambda over 2 pi because we remember how to do fractions. We are competent engineers / scientists. Same thing, right? So this is useful. I mean, it's not necessary because if you have omega and k, you can get the other stuff, but it's just kind of, it can be a shortcut. Ooh, I got an email. Okay. So let's look at our equation again. Okay, we got our k, we got our omega. We have 2 things we have not yet talked about. And we have 10 minutes left. I think that's fine. We have this bit and we have this bit. Let's talk about the plus or minus first. Plus or minus. What is the deal? What's the deal with the plus or minus? Okay, so to do that, let's talk about, so we have sine of some stuff. That's kind of basically our equation. We have D equals A sine stuff. Okay, what does this stuff have to equal? When our wave is at a crest. It does have to do with the direction of the wave. Skylar, the positioning of the graph is the question mark at the end. We're going to talk about in a second. Okay. So, what does this stuff have to equal in order for me to get a crest at some particular x and t? This stuff has to equal what? 5, -2, 1 3/4. Okay, Logan says pi over 2. Right? Because when you have sine of pi over 2, that equals 1. So a sine pi over 2 equals a. Okay, is that the only value? Or are there other values? So Andre, you're close. It's not every odd multiple. What happens at 3 pi over 2? Think about our unit circle. Okay. This is sine of 0. Oop. This is sine of pi over 2. Gives us 1. Sine of pi gives us 0. Sine of 3 pi over 2 gives us -1. Yeah. 3 by 2 gives us -1. Good. No, Logan. So we come back around to 2 pi. Gives us 0. So this one is going to be 5 pi over 2. All right, and then we come around again, and the next one is going to be at every other odd multiple. Pi over 2, 3 pi over 2, 5 pi over 2, etc. Okay, so this is what value goes in for this wiggle. Right. This wiggle actually has a name. Wiggle is what's inside the sign. Right, that's what I mean by wiggle, if that's not clear. Wiggle is actually something we call the phase. Phase. And it gets its own variable. Phase. Okay. So the wave is at a crest at the x and t values for which phi is equal to pi over 2, 3, not 3, 5 pi over 2, 7 pi over 2, etc. Okay, so Logan suggests a formula, which is pi over 2 plus, I'm not going to use k because we're using k for something else. Pi times n, but I don't think this is right. I think it has to be 2 pi times n. Does that make sense? Right, because pi over 2 plus pi would give you 3 pi over 2, which is -1. So it has to be, you have to add 2 pi every time. Right. You heard the term phase before? Might be in a physics context, might be in another context. Yes. Long ago. The one I want you to think of is phases of the moon. All right, what are the phases of the moon? This is like 5th grade right here. Okay. Waxing, waning. Okay, those are part of it. There's a full moon. Okay, do not look at which way the moon goes because I cannot for the life of me ever remember which way the moon goes, but we go full moon, and then we have part of it is in shadow. Wane is W-A-N-E, but you're close. Waxing, waning, full, new, gibbous, yeah, okay. So we have that, we have sort of half moon, We have where all this is dark. I can definitely draw. We have when it's all dark. We have when we have a light bit on this side. We have half of it is light, where most of it is light, and then we come back around to a full moon. Okay, so the names, I'm going to type them because I'm getting tired of writing. So we have full moon. We have, this is a waning gibbous. This is not going to be on your test. I think this is just called a half moon. I don't think it gets a special name. This is a waning crescent. What do we call this one where it's all dark? You should know that one. No moon, close. New moon. Okay. Then we have waxing crescent. We have another half moon that I don't think gets a name. It might be called a waxing half moon. I have no idea. Okay, wait. Tab. Okay, stop. Half moon. Waxing gibbous. I can spell gibbous. And then back to full moon again. Okay, so these are our phases. Twilight. Yes, like twilight. So I tend to think of these as corresponding to like a crest, and then this would be a trough, this would be a crest, this would be the point where it crosses the axis, right? So you can talk about what phase is it? Oh, it's a crest. What phase is it? Oh, it's a trough. You can also say, what is the phase in terms of the value of phi? So this would be pi over 2, this would be pi, this would be 3 pi over 2, this would be 2 pi, right? And it goes around. So this might be day 1, this might be day 7, this might be day 14, day 21, day 28, but this could just as easily be, oh, this is 28, this is 35, this is 42, this is, can I keep adding? 749, this is 56, first quarter and last quarter. That makes sense. I don't know how to do it. Can you believe I have a degree in astronomy? Moon math is hard. That should go in the quotes. So the phase can be anything that agrees with this, gives us a crest. You might also see it written as n plus a half times 2 pi, right? That's a way to do it. A trough would be 3 pi over 2 plus 2 pi, and a 0 would be pi plus, it's just pi times n really, for 0. Is making sense? So when we talk about the phase of the wave, we're talking about both this kind of concept and the number in radians that corresponds to that point in the progression. 2 pi would be right here, the 0, and then this would be 5 pi, the next crest. How is this feeling? Because this is really important. Phase is going to dominate everything we do for the rest of the semester, which is only like a week and a half, but still. Right? This concept of phase. Okay. So phase, as we recall, is the wiggle. It is everything inside the sign. What is this symbol that I'm drawing? don't think we talked about that. What's that symbol? Phi. You were correct. Is the lowercase phi. Uppercase phi is flux. Lowercase phi is like this. Circle with a stick. Yeah, it's in a very rotund stick man. Gamma is this one. Empty set. Lowercase phi. You may also see it written like this. That's how it's printed in some textbooks. Those are the same thing. It's just kind of cursive versus print. Kind of. Okay. So everything inside the sign. So it is our kx plus or minus omega t plus our little unknown thing. So the plus or minus, if you give me like 2 more minutes, I think I could talk about both of these and then that life will be good. So the plus or minus is like to get a crest. If we're looking at a crest, let's say our wave has a crest at x equals 0, t equals 0. And we think about, okay, kx plus omega t or kx minus omega t. If our wave is moving as time goes on, okay, t is always going up. Hopefully that is logical. So this quantity is always getting bigger. For a wave that is traveling right, okay, our crest is moving from here to here, right? So over time, right, it has moved over here. So I want to get the same value for my phase at a higher time and at a higher x. So that's only possible if I have a minus. So this is a wave going right. Right? So if you want these to add up to 0, it's going to be like 1 minus 1, 2 minus 2. Does that make sense? If the wave is going left, you want to get the same result at a higher time, but a lower x, right? So this might be 1, -1, 2, -2. In order to get these to equal 0, this has to be plus. I'm not overly worried if you understand this concept, but the rule is minus means it's going right, plus means it's going left. I remember it because minus is going right. You can also remember it in terms of there's 5 letters in each of these, and there's 4 letters in each of these. It's kind of whatever you want to do. Okay, last thing, almost done, I'm sorry. This question mark. Okay, we talked about the positioning of the wave. That tells us our starting position. So we have kx plus or minus omega t plus phi naught. Phi naught is our initial phase. So it tells us what the wave is doing at x equals 0, t equals 0. So if I go back to my Desmos graph and I take one of these, I like this one. Let's make this a little smaller. Okay. if I add an initial phase of pi over 2, that means, let me do them separately so you can see the difference. Two pi over 3x plus pi over 2. All it did was shift it over. So instead of starting at 0, it starts at a crest. Its initial phase is pi over 2. If the initial phase is negative pi over 2, it starts at a trough. If the initial phase is 57 pi over 2, hey, it's the same as starting at a crest because it's comes out to being a precise number of rotations back, right? If it was 55 pi over 2, it would be like that. If it was 54 pi over 2, it would be like that. Okay. Does this all make sense? This is where just what I wanted to get through today. I know I went a little bit over. I'm sorry. I did have some technical issues. Questions about any of this? Yay! Phase is hard. This is something a lot of students struggle with, so I really want to make sure it's like in there. Okay. So did you all see the announcement on the recitation section that you will have an opportunity to make up or retake the Physics 2 test on, I believe, Wednesday? You don't have to. If you're happy with your grade, you can keep it. If you would like another chance, you can do that. Your homework will apply to whichever one you do better on. So it will be different questions. We're not that kind. So the thought is that we would like students to have a chance at, because it was the first test that you took with Proctorio, we want you to have an opportunity to try it again and sort of see. Yeah. Not that I know of. I can ask. So one thing I've noticed, I think students, might do this on purpose. I'm not accusing anybody. Oh, that's true. We did not do, it wasn't a common exam. So it's possible that, you all had a different exam than everybody else. You also had a higher average by about 12 points. I think it's because you're awesome. But it's possible that they may have curved to make up for that discrepancy. They were like, oh, maybe Astley gave an easier test, so we're going to curve to make up for it. I don't think it was an easier test, but it's just me. Yeah, I think you're just good. But I can ask them about it. Yeah. So Noelle also asked me about, and I think Skylar asked about final homework. There is a final homework packet, but I am not quite sure what I am doing with it. Because did you also see, I think the final exam will replace your lowest test grade? Did we announce that yet? Yeah, I did mention it in passing. There will be something, but it's not going to work the same way. It's not going to go like, it's not going to be like the 20% like we've done. Let me check. I don't know if I was supposed to announce that yet. But we talked about it. I thought we decided that's what we were doing. Let me check my email. Yeah, I'm like 90% sure. It's not in the announcement. I don't see it. I think that's all we decided. Okay. Pretend I didn't say that. Shh. See. But yeah, that is what I believe we agreed to. So hopefully that's what's going to happen. It's fine. So you'll find out soon. It's good. But yes, definitely do the retake if you're interested. What else? There will be a final homework in some form that will be some form of bonus. What exactly that form will be, I don't know. What I've done in the past is made it be just like bonus points for something. We'll find out. I have to figure out what they'll let me get away with. Oh, you know what? This is recorded, so you can always go back and watch the recording of me going, shh. Okay. Any other questions about anything before I let you go? I will try to post like a little Canvas quiz for you, but it might not go up until tomorrow. And I know I haven't graded anything in like forever, but someday. Probably not for a while. Also, homework. What about homework? When I'll give it to you, or when it'll be graded, or when it'll be due, or all of the above. Homework will be graded before the heat death of the universe. That's the most I'm willing to promise at this point. There's only so long I can sit in this chair every day. And I'm grading tests and things. That's my problem. What else am I doing? I will post the final homework soon. I'll put that on my to-do list for the weekend. And it'll be due. Usually, I do it when you take the final exam. Yeah, no, that's fair. I will try to post it. Mm-hmm. All right. Anything else? I'm starting to write stuff down. That helps. Otherwise, I just. Okie dokie. Everyone's leaving. Okay. Bye, everybody. Have a lovely weekend. Don't work too hard. Hang up. Hang up. All right. Yeah. See you next week. Bye.